You're not going to expect this.
Okay, I'm doing the mini, so I hope I'm not surprised by the mini. Anyhow, these ducks, they would really like this episode. They would be really impressed with what I'm about to tell you.
Well, that makes me more excited.
Yeah, I don't know. Those ducks seem pretty impressed very easily. Anyhow, sorry guys, you're not involved with the eider ducks, so don't worry about them. Chelsea, not a source I use very often, sciencealert.com.
Oh, that sounds official.
Yeah, this is written by Enrique Gastanaga on June 5th, 2025. Article title, Big Bang may not be the beginning of everything, new theory suggests.
Oh, what is it?
The Big Bang is often described as an explosive birth of the universe, a singular moment when space, time, and matter sprang into existence. But what if this was not the beginning at all? What if our universe emerged from something else? Something more similar and radical at the same time. In a new paper published in Physical Review, my colleagues and I propose a striking alternative. Our calculations suggest the Big Bang was not the start of everything, but rather the outcome of a gravitational crunch or collapse that formed a very massive black hole, followed by a bounce inside. The idea, which we call the black hole universe, offers a radically different view of cosmic origins. Yet it is grounded entirely in known physics and observations. Today's standard cosmological model, based on the Big Bang and cosmic inflation, has been remarkably successful in explaining the structure and evolution of the universe, but it comes at a price. It leaves some of the most fundamental questions unanswered. For one, the Big Bang model begins with a singularity, a point of infinite density where the laws of physics break down. This is not a technical glitch, it's a deep theoretical problem that suggests we don't really understand the beginning at all. To explain the universe's large-scale structure, physicists introduce a brief phase of rapid expansion into the early universe called cosmic inflation, powered by an unknown field with strange properties. Later, to explain the acceleration observed today, they added another, quote, mysterious, unquote, component, dark energy. In short, the standard model of cosmology works well, but only by introducing new ingredients we have never observed directly. Meanwhile, the most basic questions remain open. Where did everything come from? Why did it begin this way? And why is the universe so flat, smooth, and large? Our new model tackles these questions from a different angle, by looking inward instead of outward. Instead of starting with an expanding universe and trying to trace back how it began, we consider what happens when an overly dense collection of matter collapses under gravity. This is a familiar process. Stars collapse into black holes, which are among the most well-understood objects in physics. But what happens inside a black hole, beyond the event horizon from which nothing can escape, remains a mystery. In 1965, the physicist Roger Penrose proved that under very general conditions, gravitational collapse must lead to a singularity. This result, extended by the late British physicist Stephen Hawking and others, underpins the idea that singularities like one at the Big Bang are unavoidable. The idea helped win Penrose a share of the 2020 Nobel Prize in Physics and inspired Stephen Hawking's global bestseller, A Brief History of Time from the Big Bang to Black Holes. But there's a caveat. Their, quote, singularity theorems, end quote, rely on, quote, classical physics, end quote, which describes ordinary macroscopic objects. If we include the effects of quantum mechanics, which rules the tiny microcosmos of atoms and particles, as we must at extreme densities, the story may change. In our new paper, we show the gravitational collapse does not have to end in a singularity. We find an exact analytical solution, a mathematical no approximations. Our maths show that as we approach the potential singularity, the size of the universe changes as a hyperbolic function of cosmic time. The simple mathematical solution describes how a collapsing cloud of matter can reach a high density state and then bounce, rebounding outward into a new expanding phase. But how come Penrose's theorem forbid out such outcomes? It all comes down to a rule called the quantum exclusion principle, which states that no two identical particles known as fermions can occupy the same quantum state, such as angular momentum or spin. And we show that this rule prevents the particles in the collapsing matter from being squeezed indefinitely. As a result, the collapse halts and reverses. The bounce is not only possible, it's inevitable under the right conditions. Crucially, this bounce occurs entirely within the framework of general relativity, which applies to large scales such as stars and galaxies, combined with the basic principles of quantum mechanics. No exotic fields, extra dimensions, or speculative physics required. What emerges on the other side of the bounce is a universe really like our own. Even more surprisingly, the rebound naturally produces the two separate phases of accelerated expansion, the inflation and dark energy, driven not by a hypothetical field, but by the physics on the bounce itself. That's probably as far as I need to go. There's a bit more, but it's a little too sciencey, so we can end it there.
It was pretty sciencey.
Yeah. Anyhow, this is somehow weirdly what I've always kind of understood the Big Bang to be, is basically our universe came from the creation of a black hole in a bigger universe. And that's where the Big Bang comes from.
So it's another kind of, what would you call that? Like a mirror.
We're a universe within a universe created by a black hole creating. Yeah.
Yeah. It's hard to picture something coming from nothing, to be honest. But with that, I will counter you with whales come from wolves.
They do, but black holes do not. I understand now.
They actually might come from wolves.
I don't think they do.
Am I not understanding
I
the whole
just don't think the
concept
evolution line comes to that.
correctly?
It might be wolves the whole way down. I don't know for sure.
I feel like it's wolves the whole way down.
I heard it was turtles, but it may be wolves the whole way down.
I feel like it's wolves.
But does that not make it infinitely easier to envision the Big Bang as like, oh yeah, it's just the creation of a black hole?
I feel like whatever it is not going to make sense to our mind. Whatever it is.
Well, you have to remember too, it would be the creation of a black hole in a universe above us, which would have different physics rules. Because our rules of physics will only apply within our event horizon.
What is the theory of the 9 different universes? What is that again? Where we're like bubbles within string?
No, that's not string theory. Is that string theory?
String theory?
I thought there was like 15 different
Maybe it's 15.
levels.
I think it is string theory, but maybe it exists within that. But it's just so hard. I'm not a physicist. I can barely wrap my head around how big space is. And I don't know.
That's okay.
Maybe
Nobody
there
can.
is.
You just don't know how to ignore that.
I welcome other theories other than the Big Bang theory.
But this isn't really
Which
a
is
different
nice.
one. It's just saying that the Big Bang was a black hole created.
Yeah.
Which doesn't mean we can forget about that point in time. It just means that that point in time was a black hole created.
Yeah.
Anyhow, that's probably enough math and or physics and or
I don't
space
know
talk.
if I'm going to be able to do the episode this week. Give me 48 hours.
Yeah, you guys got 48 hours to get better.
I need 48
Chelsea does
hours.
not. So she does, but too bad. She's got to do it. Anyhow, bye.
Bye.